Time doesn't tick the same everywhere. Right now, time moves faster or slower depending on where you are. You assume time flows at one steady pace. That assumption is completely wrong. Tonight we're discovering why time bends and warps, and how this invisible effect controls technology you use every day. Before we dive into this warped reality, drop a comment about where you're listening from. If you enjoy these mind-bending physics journeys, consider subscribing. For 300 years, one man ruled physics completely. Isaac Newton declared that time flows the same everywhere. Past, present, future marched forward at identical rates. Whether you stood on Earth or drifted through empty space, every scientist accepted this as obvious truth. Clocks measured time. Time existed independently of everything else. The entire universe ran on one giant, invisible clock. Then Albert Einstein arrived with devastating math. Two American scientists performed a simple experiment in the late 1800s. They tried measuring how Earth moves through space by studying light beams. Instead, they discovered something impossible. Light travels at exactly the same speed, no matter which direction you point it. This broke Newton's rules completely. Einstein provided the shocking answer. Time and space aren't separate things. They're woven together into one stretchy fabric that bends and warps around massive objects. Move fast enough, and time genuinely slows down around you. This isn't a metaphor. Scientists have measured this effect with the most precise clocks ever built. The faster you travel through space, the slower you move through time. At everyday speeds, this effect stays completely invisible. Your morning commute doesn't make you age any slower. But approach the speed of light, and something incredible happens. Scientists smash tiny particles around giant underground racetracks. These particles normally live for about 2/millionths of a second before disappearing. When accelerated to near light speed, the same particles survive dozens of times longer from our perspective. Their internal clocks literally run slower because they're racing through space. At 90% light speed, time crawls to half its normal rate. This represents real physics that governs every corner of our universe. Gravity doesn't just pull objects downward. Gravity reaches into time itself and slows it down. The stronger the gravitational pull around you, the slower your personal time flows compared to everyone else. Einstein predicted this impossible-sounding effect. Time runs slower on Earth's surface than it does high above in orbiting satellites. The difference seems tiny, but it's measurable with atomic clocks. Scientists proved this by flying super-accurate timepieces around the world in airplanes. When they landed, the flying clocks had fallen slightly behind identical clocks that stayed on the ground. This happens because massive objects like Earth actually warp the fabric of space and time around them. Think of a bowling ball placed on a stretched rubber sheet. The ball creates a dip that affects everything nearby. Massive planets and stars create similar dips in the fabric of time itself. Your smartphone navigation depends entirely on correcting time distortion effects. Without accounting for time's weird behavior, GPS would be useless within hours. The satellites orbiting overhead experience time differently than you do down here on Earth's surface. GPS satellites circle our planet at tremendous speeds while sitting in weaker gravity than we experience. Both effects alter how time flows for these orbiting clocks. Speed makes their time slow down. Weaker gravity makes their time speed up. Engineers must calculate both effects precisely and adjust the satellite clocks accordingly. Without these corrections, GPS errors would grow by several miles every single day. Every time you get driving directions, use a rideshare app, or track your morning jog, you're benefiting from Einstein's insights about time's malleable nature. The most practical technology relies on the universe's most mind-bending physics. In the 1970s, two physicists performed the ultimate test of Einstein's time predictions. They loaded super-precise atomic clocks onto commercial airliners and flew them around the world in opposite directions. When the planes landed, something extraordinary had happened. The eastbound clocks had lost time compared to reference clocks on the ground. The westbound clocks had gained time. Both results matched Einstein's equations perfectly. This wasn't measurement error or equipment malfunction. Time had genuinely flowed at different rates for the flying clocks versus the stationary ones. Today, particle accelerators around the world confirm these effects thousands of times per second. Subatomic particles racing at near light speed consistently live longer than identical particles at rest. Their rapid motion literally stretches their lifespan from our perspective. Time dilation isn't abstract theory anymore. It's proven reality that operates throughout our universe. You can't reach the speed of light. Physics makes this impossible. But something incredible happens as you get closer and closer to that ultimate speed limit. Scientists call this the Lorentz factor. It's a mathematical formula that predicts exactly how much time slows down at any given speed. At everyday speeds, this number stays close to 1. Time flows normally. But push toward light speed, and this factor explodes upward like a rocket. At 50% light speed, time slows by about 15%. At 90%, time crawls to half its normal rate. At 99% light speed, time slows to 1/7 normal speed. The mathematical curve shoots toward infinity as you approach that ultimate barrier. This exponential growth explains why nothing with mass can ever reach light speed. The closer you get, the more dramatically time dilates around you. Tiny particles called muons rain down from space constantly. These subatomic specks normally self-destruct in just over 2 microseconds. That's barely enough time to travel a few hundred meters before vanishing completely. Yet muons created high in Earth's atmosphere somehow reach the ground level where we can detect them. This should be impossible given their incredibly short lifespans and the vast distance they must travel. Special relativity solves this puzzle perfectly. These cosmic moons streak through our atmosphere at nearly light speed. From our perspective watching from Earth, their internal clocks tick much slower than normal. What feels like 2 microseconds to the muon translates to roughly 14 microseconds in our reference frame. This extra time allows them to complete their journey from the upper atmosphere to ground level before decaying. Moving clocks literally tick slower, extending the particle's effective lifetime. Imagine launching on a round trip to a nearby star system. Your spacecraft accelerates to 80% light speed for the entire journey. The destination lies 20 light years away, requiring a 40-year round trip at this tremendous velocity. When you return to Earth, something shocking awaits you. 40 years have passed on your ship's clocks and in your personal experience. But Earth's calendars show that 67 years have elapsed. Your high-speed journey literally transported you into Earth's future. This isn't science fiction speculation. Time dilation calculations produce precise predictions for any speed and distance combination. The faster and longer you travel, the further into Earth's future you emerge upon return. Astronauts already experience tiny versions of this effect during orbital missions, aging microseconds less than people on Earth's surface. Two lightning bolts strike simultaneously at opposite ends of a moving train. Observers standing on the platform see both flashes occur at exactly the same moment. This seems like an absolute fact that everyone should agree upon. But a passenger riding inside the train observes something completely different. From her perspective, the lightning bolt at the front of the train strikes first. The rear lightning bolt follows slightly later. Both observers are completely correct within their own reference frames. Einstein's relativity demolishes the concept of absolute simultaneity. Events that appear simultaneous to one observer occur in sequence to another observer moving at a different velocity. The faster the relative motion, the more pronounced this effect becomes. This means the universe has no universal now that applies everywhere simultaneously. Time and space aren't separate, independent dimensions. They're different aspects of a unified four-dimensional fabric called spacetime. What you measure as a time interval, someone else might measure as a spatial distance. Consider two events. A light bulb turning on and off. If you're sitting next to the bulb, you measure these as two events separated only in time. The bulb occupies the same location, but flashes at different moments. But imagine observing the same bulb while traveling past it at high speed. From your moving perspective, the light bulb travels a significant distance between turning on and off. What appeared as pure time separation now includes a spatial component. The on and off events are separated in both space and time from your reference frame. This space-time mixing becomes more extreme at higher relative velocities, fundamentally changing how different observers carve up reality into space and time coordinates. Stand inside a windowless elevator. Someone accelerates the elevator upward at a steady rate. You feel pressed against the floor with exactly the same sensation as standing on Earth's surface under gravity's pull. Einstein realized something profound about this similarity. You cannot perform any experiment inside that elevator to distinguish between gravitational acceleration and mechanical acceleration. They produce identical physical effects on everything inside. This equivalence principle leads to a startling conclusion about time itself. If acceleration slows down time, then gravity must slow down time by exactly the same amount. An accelerating rocket ship experiences time dilation. Therefore, sitting in Earth's gravitational field must also dilate time compared to floating in empty space. This prediction launched Einstein toward his theory of general relativity, where massive objects warp the fabric of spacetime itself. Climb to the top of Mount Everest with an atomic clock. Compare it to an identical clock left at sea level. After just one day, the mountain clock runs slightly ahead of the sea level clock. This happens because gravity weakens with altitude. The higher you climb, the weaker Earth's gravitational pull becomes. Weaker gravity means time flows slightly faster relative to stronger gravitational fields below. The difference measures only billionths of a second per day, but modern atomic clocks detect this tiny discrepancy easily. GPS satellites orbit at an altitude where Earth's gravity is significantly weaker than at ground level. Their onboard clocks tick about 45 microseconds faster per day than identical clocks on Earth's surface. Engineers must account for this gravitational time difference, or GPS navigation would become useless within hours. This altitude effect proves that gravity directly controls the rate at which time passes. Light escaping from the sun's surface faces a tremendous gravitational climb. As photons fight their way out of the sun's deep gravitational well, something remarkable happens to their energy and color. the light loses energy during this upward journey. Lower energy means longer wavelength. Longer wavelength shifts the light toward the red end of the spectrum. This gravitational redshift provides direct evidence that gravity affects time itself, not just massive objects. Scientists measured this effect by comparing the wavelength of light emitted from the sun's surface with identical light produced in Earth-based laboratories. The solar light consistently shows longer wavelengths, exactly matching Einstein's predictions. This redshift occurs because time runs slower in stronger gravitational fields. From the perspective of distant observers, processes near massive objects appear to slow down, including the oscillation rate of light waves. Einstein's field equations describe how mass and energy curve the geometry of spacetime. These mathematical relationships connect the amount of curvature directly to the strength of gravitational time dilation effects. Picture a rubber sheet stretched tight. Place a bowling ball in the center. The sheet curves downward around the ball, with the steepest curves closest to the ball's center. Spacetime behaves similarly around massive objects like stars and planets. The curvature of space automatically determines how much time slows down at any given location. Steeper curvature means stronger time dilation. Flatter regions experience faster flowing time relative to curved areas. This geometric relationship explains why time runs slower on neutron stars than around normal stars. Neutron stars pack enormous mass into tiny volumes, creating extreme space-time curvature that dramatically slows time throughout their neighborhood. Strong gravitational fields don't just slow time uniformly. They create time gradients where different parts of the same object experience slightly different rates of time flow. Scientists call these variations tidal effects. Consider a spacecraft falling toward a black hole. The crew member closest to the black hole experiences stronger gravity than the crew member farthest away. This difference means time flows at minutely different rates across the length of their ship. These tidal time effects become extreme near ultramassive objects. For someone falling toward a black hole's event horizon, the time gradient becomes so steep that their feet literally experience noticeably slower time than their head. This differential stretches the falling person like taffy while simultaneously creating a temporal gradient across their body. This effect demonstrates that gravity doesn't just warp time uniformly. It creates complex, position-dependent time flows that vary across space. Every GPS satellite orbits Earth while experiencing two opposing time effects simultaneously. High orbital speed tries to slow their clocks down. Weaker gravity at altitude tries to speed their clocks up. These competing forces create a complex timing problem that engineers must solve every second of every day. Without precise calculations, your navigation apps would guide you into walls within hours. Speed wins part of this battle, gravity wins the other part. GPS satellites travel at roughly 14,000 miles per hour in their orbital dance around Earth. This tremendous velocity causes their onboard atomic clocks to tick about 7 microseconds slower per day compared to identical clocks on the ground. But gravity delivers the knockout punch in the opposite direction. At orbital altitude, Earth's gravitational pull weakens significantly. This weaker gravity allows satellite time to flow 45 microseconds faster per day than ground-based time. Turn off relativistic corrections in the GPS system for just one day. Watch civilization's navigation infrastructure collapse in real time. Within 6 hours, GPS accuracy degrades from meter-level precision to errors measuring hundreds of meters. emergency services lose the ability to locate accident victims. Commercial aviation faces safety crisis as instrument landing systems fail. By day's end, position errors exceed several miles in every direction. This catastrophic failure stems from accumulated timing errors between satellites and ground receivers. GPS works by precisely measuring how long radio signals take to travel from satellites to your device. Even microsecond timing errors translate to massive distance miscalculations. Modern society depends entirely on Einstein's time dilation equations, running silently in the background of every GPS receiver ever manufactured. Scientists now build clocks so precise they would not lose a single second over timescales comparable to the age of the universe. These optical lattice clocks detect gravitational time differences across distances as small as a few centimeters of altitude change. These devices trap individual atoms in grids of laser light. The atoms oscillate at frequencies measured in hundreds of trillions of cycles per second. Scientists count these oscillations to track time with unprecedented accuracy. Such precision reveals relativistic effects everywhere around us. These super clocks detect the tiny time difference between your head and your feet caused by Earth's gravitational gradient. They measure time dilation effects from moving just a few miles per hour in any direction. Every elevator ride, every flight of stairs, every car trip produces measurable changes in time's flow rate. This technology opens entirely new fields of precision physics and ultra-accurate navigation systems. Communication satellites, weather satellites, and spy satellites all face the same fundamental problem. Their onboard clocks drift away from Earth-based time standards due to relativistic effects. Without constant time corrections, satellite networks lose the ability to coordinate with ground stations. Data transmission windows miss their targets. Satellite constellations fall out of sync with each other. The solution requires continuous monitoring and adjustment of every orbital timekeeper. Ground control centers track each satellite's velocity, altitude, and orbital path in real time. Computers calculate the exact relativistic corrections needed for each spacecraft based on its current motion and gravitational environment. These corrections are uploaded to satellites multiple times per day. This synchronized dance between relativity theory and engineering keeps modern satellite technology functioning properly across hundreds of orbital platforms. Atomic clocks scattered across Earth's surface don't all tick at identical rates. Differences in altitude, latitude, and local gravitational conditions create tiny timing variations between these precision instruments. International time standards require combining signals from dozens of these clocks into one coordinated global time reference. This process demands accounting for relativistic effects at every participating location. The differences seem impossibly small, but matter enormously for global infrastructure. A clock in Denver runs slightly faster than an identical clock in New York due to Denver's higher altitude above sea level. Clocks near Earth's equator experience different effects from planetary rotation compared to clocks at the North Pole. Scientists measure and correct for all these relativistic variations to maintain coordinated universal time as the planet's official timekeeper. Two physicists loaded the world's most accurate clocks onto commercial airliners in 1971. Hafeel and Keating flew these atomic timepieces around the entire planet in opposite directions. Meanwhile, identical reference clocks stayed safely on the ground. The flying clocks should have kept perfect time if Newton's absolute time were correct. Instead, they returned with measurable time differences that matched Einstein's predictions exactly. This marked the first direct proof that moving clocks actually tick slower than stationary ones. The eastbound clocks lost about 200 nanoseconds compared to the ground-based references. The westbound clocks gained nearly 300 nanoseconds. Both results fell within the narrow range that relativity equations predicted for their specific flight paths and speeds. These airplane experiments transformed time dilation from abstract theory into concrete, measurable reality that anyone could verify with sufficient precision instruments. Astronauts aboard the International Space Station live in a constant state of mild time dilation. They orbit Earth at roughly 17,000 miles per hour while experiencing slightly weaker gravity than people on the surface. Every 6-month mission ages the crew members microseconds less than their Earth-bound counterparts. The effect accumulates continuously throughout their orbital stay. This represents humanity's longest sustained experience with relativistic time effects. The space station circles our planet once every 90 minutes at an altitude where Earth's gravitational pull weakens noticeably. High orbital speed slows their personal time down. Reduced gravity speeds their personal time up. The speed effect dominates slightly, creating a net time delay. Astronauts return from long missions, having literally traveled a tiny distance into Earth's future compared to people who remained on the ground. Deep underground in Switzerland, scientists accelerate subatomic particles to nearly light speed inside a circular tunnel stretching 17 miles around. These particles experience extreme time dilation effects that researchers can measure with perfect precision. Particles called pions normally self-destruct in about 26 nanoseconds when at rest. But when accelerated to 99% light speed, these same particles survive for hundreds of nanoseconds before decaying. This represents the most precise verification of special relativity ever achieved. The Large Hadron Collider and similar facilities around the world confirm time dilation predictions millions of times per day. Every high-energy collision produces particles that live exactly as long as Einstein's equations predict, based on their measured velocities. Modern particle physics depends entirely on relativistic calculations to predict experimental outcomes and design new detection systems. What happens to time-near objects so dense that a teaspoon of their material would weigh as much as Mount Everest? Neutron stars provide natural laboratories for studying extreme gravitational time effects that dwarf anything achievable on Earth. These collapsed stellar cores pack more mass than our Sun into spheres smaller than major cities. Their surface gravity creates time dilation effects millions of times stronger than anything we experience. Radio telescopes detect regular pulses from these spinning neutron stars as they sweep beams of radiation across space like cosmic lighthouses. When neutron stars orbit each other in binary pairs, scientists observe their orbital periods gradually slowing down. This deceleration matches predictions for energy loss through gravitational wave radiation, providing indirect evidence of space-time distortion effects. These observations confirm that extreme gravity produces correspondingly extreme time dilation throughout the universe's most massive objects. Laser interferometers designed to detect gravitational waves measure distances with precision beyond human comprehension. These instruments track length changes smaller than 1/10,000th the width of a proton as gravitational waves pass through Earth. Such extreme precision requires accounting for every possible source of timing error, including relativistic effects on the laser light itself. Gravitational waves don't just stretch and compress space. They also modulate the flow of time. Scientists must correct for these temporal variations to achieve the sensitivity needed for gravitational wave detection. The LIGO and Virgo detectors incorporate relativistic corrections into every measurement. Without these adjustments, background noise from time fluctuations would completely overwhelm the tiny signals produced by colliding black holes billions of light years away. Gravitational wave astronomy represents the ultimate fusion of Einstein's relativity theory with cutting-edge experimental technology. Identical twins celebrate their 20th birthday together. One twin boards a spacecraft bound for a star system 20 light-years away. The other twin stays home on Earth to live a normal life. The traveling twins' journey takes 40 years round trip as measured by Earth's calendars. When the spacecraft returns, the Earth-bound twin has aged 40 years and now celebrates his 60th birthday. But the space-traveling twin steps off the ship, having aged only about 24 years. The high-speed journey through space literally transported the traveler into Earth's future. At 80% of light speed, time dilation reduces the aging process significantly for the moving twin. While Earth experiences 4 decades, the spacecraft experiences roughly 2.5 decades. This age difference represents genuine time dilation, not science fiction fantasy. Why doesn't the stationary twin also age less from the traveler's perspective? This question puzzled physicists for decades after Einstein first proposed special relativity. The answer lies in the acceleration phases when the spacecraft changes direction. During these periods, the traveling twin experiences forces that break the symmetry between reference frames. Special relativity only applies cleanly to constant velocity motion, not accelerated motion. When the spacecraft turns around at the halfway point, the traveler experiences tremendous acceleration forces. From the accelerating twin's perspective during this turnaround, Earth's clocks appear to run extremely fast, accumulating the extra years needed to resolve the paradox. This acceleration phase ensures that only the traveling twin returns younger, making the age difference absolute and unambiguous. From inside the turning spacecraft, something extraordinary happens to time on distant Earth. As the ship reverses direction at the halfway point, Earth's clocks appear to accelerate dramatically. During most of the outbound journey, Earth's clocks tick slower than the spacecraft's clocks from the traveler's perspective. The same pattern occurs during the return journey home. But during the brief turnaround period, this relationship flips completely. From the accelerating spacecraft's viewpoint, Earth's time jumps forward by roughly 16 years during the turnaround maneuver. This rapid advancement compensates for all the slow time that accumulated during the constant velocity portions of the journey. The traveling twin observes Earth aging faster during acceleration, explaining why the Earth twin ends up older despite appearing to age slowly during most of the trip. Scientists cannot send human twins on interstellar journeys, but they can create twin particles and accelerate one of them to near light speed. Particle accelerators perform these experiments millions of times per day. Researchers create identical subatomic particles in laboratory conditions. One particle remains at rest while its twin gets accelerated to tremendous velocities around circular tracks. The accelerated particles consistently live longer than their stationary twins, exactly as the twin paradox predicts. These particle-twin experiments prove that acceleration creates asymmetric aging effects. The accelerated particles experience time dilation that extends their lifespans far beyond what stationary particles achieve. Every measurement confirms Einstein's predictions about differential aging between accelerated and inertial reference frames. Modern physics has transformed the twin paradox from thought experiment into measurable reality using subatomic stand-ins for human travelers. Special relativity alone can describe much of the twin paradox, but a complete analysis can also use Einstein's general theory of relativity, which describes how acceleration and gravity relate to spacetime geometry. During acceleration phases, the spacecraft creates artificial gravitational fields that affect time flow. These effects combine with special relativistic time dilation to produce the final age difference between twins. General relativity can treat acceleration using the same language it uses for gravity in terms of spacetime geometry. The accelerating spacecraft experiences spacetime conditions similar to strong gravitational fields. Time flows differently in these conditions compared to flat spacetime. When combined with velocity-based time dilation, these effects ensure that the traveling twin ages less overall. This complete relativistic analysis shows that time dilation emerges from the fundamental geometry of space and time throughout the universe. Watch someone fall toward a black hole from a safe distance. As they approach the event horizon, something impossible appears to happen. Their motion slows down dramatically from your perspective. The event horizon marks the boundary where nothing, not even light, can escape the black hole's gravitational grip. This invisible sphere surrounds the black hole like a one-way membrane in space. Near this boundary, time dilation reaches its most extreme possible values. From your distant vantage point, the falling person's clocks appear to tick slower and slower as they approach the point of no return. Their final moments stretch out over hours, then days, then years from your perspective. Their image freezes at the event horizon, appearing motionless for eternity. This represents the most extreme time dilation effect possible in our universe, where gravity's pull becomes so intense that time itself nearly stops relative to distant observers. From the perspective of someone actually falling into a black hole, time flows completely normally. Their wristwatch ticks at regular intervals. Their heartbeat maintains its usual rhythm. They experience no sensation of time slowing down whatsoever. Yet something far more disturbing happens when they look outward toward the rest of the universe. Stars appear to speed up their evolution. Planets complete orbits in fast forward motion. The falling observer watches billions of years of cosmic history unfold in what feels like hours. This extreme time differential occurs because the falling person moves deeper into the black hole's gravitational time well. While their personal time flows normally, the external universe experiences vastly accelerated time from their perspective. They witness entire civilizations rise and fall during their final descent. The falling observer literally watches the future of the universe while experiencing their own normal passage of time. Material spiraling into a black hole doesn't fall straight down. Instead, it forms a massive rotating disk called an accretion disk. This cosmic whirlpool stretches across distances larger than our entire solar system. Different parts of this disk orbit at different distances from the black hole's center. The inner edge races around the black hole at nearly light speed. The outer regions move more slowly through weaker gravitational fields. This creates a complex gradient where time flows at different rates across the disk. Matter in the inner disk experiences severe time dilation compared to material in the outer regions. Gas clouds that started their inward journey simultaneously become separated in time as well as space. The inner material ages more slowly than outer material, creating temporal shear across the entire structure. This time gradient helps explain the complex physics of matter heating up and radiating energy as it approaches the black hole's event horizon. When two black holes spiral into each other, they create the most violent events in the universe. These cosmic crashes generate gravitational waves that ripple outward through space-time at light speed. Scientists detect these waves using laser interferometers here on Earth. The gravitational wave signals carry encoded information about the extreme time dilation effects that occurred during the black hole merger. These wave patterns provide direct evidence of space-time dynamics in the most extreme gravitational environments possible. As the black holes orbit each other faster and faster before merging, time dilation effects become increasingly severe near each event horizon. These temporal distortions get imprinted into the gravitational wave signal itself, creating characteristic patterns that scientists can decode. Modern gravitational wave astronomy allows us to study time dilation effects from black hole collisions that occurred billions of years ago across the observable universe. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation from their event horizons. This quantum mechanical process operates on timescales far longer than the current age of the universe. But as black holes shrink through this evaporation process, their event horizons contract inward. This changing boundary creates evolving time dilation effects that challenge our understanding of spacetime itself. Near an evaporating black hole, the traditional concepts of space and time begin to break down completely. The intersection of quantum mechanics and general relativity produces effects that require entirely new theories of physics. Time dilation calculations become meaningless when quantum uncertainty principles conflict with gravitational time warping predictions. This represents the frontier where Einstein's classical description of curved spacetime must give way to a quantum theory of gravity that scientists are still working to develop. How long does it take for a light bulb to flash on and off? This seems like a simple question with one obvious answer. But Einstein's relativity reveals that time intervals depend entirely on who performs the measurement. An observer sitting next to the bulb measures one time duration. An observer speeding past the bulb at high velocity measures a completely different time duration. Both measurements are equally valid and correct. Scientists distinguish between these two types of time measurement using special terminology. Coordinate time represents what distant observers measure using their own clocks and reference frames. Proper time represents what local observers measure using clocks right next to the events being timed. The same physical process produces different numerical results depending on which measurement method you choose. This fundamental distinction explains why relativity problems often seem paradoxical until you carefully specify who is doing the measuring and from what perspective. Step off a tall building in free fall. During your brief descent, something remarkable happens to the physics around you. All the effects of gravity temporarily disappear from your local environment. You and your pocket watch fall together at exactly the same rate. From your perspective, your timepiece ticks normally. Special relativity applies perfectly in your local reference frame, even though you're accelerating under gravity's influence. Einstein called this the equivalence principle, and it reveals something profound about proper time. Free-falling observers always measure proper time correctly for events happening right next to them. Their local measurements follow special relativity rules exactly, Only distant coordinate observers see gravitational time dilation effects affecting the free-falling clocks. This local normalcy explains why astronauts in orbit experience time flowing normally from their own perspective, even though ground-based observers measure their clocks running slow. Choose any coordinate system to describe space-time events. Switch to a completely different coordinate system with different units and orientation. Watch most measurements change dramatically between these two descriptions. Distances stretch or contract. Velocities increase or decrease. Time intervals expand or shrink. Nearly every quantity transforms when you change your mathematical coordinate system. But proper time measurements remain absolutely identical regardless of coordinate choice. This invariance property makes proper time the most fundamental way to measure temporal intervals in relativity theory. Coordinate time measurements depend on arbitrary choices about reference frames and measurement procedures. Proper time represents the genuine physical duration that nature actually implements. Scientists rely on this coordinate independence to ensure that physical laws produce the same results regardless of which mathematical description they choose to use. Accelerate a spacecraft to 99.9% of light speed. Calculate how long it takes to travel 1 light year using coordinate time measurements from Earth's reference frame. The numbers become absurd. From Earth's perspective, the journey takes nearly forever as the spacecraft approaches light speed. Coordinate time stretches toward infinity as velocity approaches the ultimate speed limit. Yet the spacecraft's onboard chronometers measure a perfectly finite journey duration. This dramatic difference occurs because coordinate time measurements break down at extreme velocities. They become mathematical artifacts rather than meaningful physical quantities. The spacecraft crew experiences proper time throughout their journey, which remains finite and well-behaved at any velocity. Proper time provides the physically meaningful measurement that corresponds to actual aging, radioactive decay, and biological processes experienced by the travelers themselves. Strip away all the mathematical abstractions and coordinate system choices from relativity theory. What remains is proper time as the bedrock foundation of temporal measurement. Your wristwatch measures proper time. Your heartbeat follows proper time. Every physical and biological process in your body operates according to proper time rhythms. Coordinate time represents a useful mathematical tool for calculations, but it doesn't correspond to any direct physical experience. When scientists discuss time dilation, they're comparing proper time measurements between different observers. The time that actually flows for any individual observer is always their own proper time. This local time always appears normal and undilated to the person experiencing it. Proper time represents the genuine temporal dimension of space-time that determines how much aging, radioactive decay, and physical change actually occurs throughout the universe. Light from distant galaxies appears redder than identical light produced in nearby laboratories. This cosmic redshift reveals something profound about time itself throughout the universe's history. As space expands between galaxies, it stretches the wavelength of light traveling through that expanding space. But this stretching effect connects directly to time dilation on cosmic scales. The redshift we observe represents a temporal fingerprint of slower time in the distant past. When astronomers observe light from galaxies billions of light years away, they're seeing those galaxies as they existed billions of years ago. But time flowed more slowly in the early universe due to its different expansion rate and energy density. This means distant observations capture not just ancient locations, but ancient time itself flowing at a different rate than our current cosmic epoch experiences. The cosmic microwave background radiation preserves a snapshot of the universe when it was only 380,000 years old. This ancient light carries temporal information about how time flowed during the universe's infancy. Back then, the universe contained much more energy packed into a much smaller volume. This higher energy density created gravitational time dilation effects that slowed the flow of time compared to today's more dilute cosmic conditions. Early cosmic time literally ran slower than modern cosmic time. The universe's expansion rate was also dramatically different during its early epochs. These changing cosmic conditions produced time dilation effects that varied throughout cosmic history. Events that lasted specific durations in the early universe would measure differently if they occurred in today's cosmic environment. This temporal evolution means the universe has experienced an accelerating passage of time as it expanded and cooled throughout cosmic history. Dark energy currently accelerates the universe's expansion at an ever-increasing rate. This mysterious force comprises about 70% of the universe's total energy content, yet scientists barely understand its nature. If dark energy continues strengthening, it could fundamentally change how time flows throughout the universe in the distant future. The accelerating expansion might create new types of cosmological time dilation effects. Different regions of space could begin experiencing dramatically different rates of time passage. As dark energy pushes space apart faster and faster, it might eventually overcome all gravitational binding forces. This could lead to a universe where time flows at vastly different rates depending on location and cosmic environment. Such temporal fragmentation would represent a completely new phase of cosmic evolution where synchronized universal time becomes impossible to maintain across different regions of space. The observable universe has a finite edge called the cosmic horizon. Beyond this boundary, light hasn't had enough time since the Big Bang to reach Earth yet. This horizon effect creates permanent temporal isolation for events occurring beyond our cosmic visibility limit. Information about those distant events will never arrive at our location. Some moments in cosmic history remain forever inaccessible due to the finite speed of light in the universe's finite age. As the universe continues expanding, this horizon actually shrinks in terms of the fraction of total space we can observe. Galaxies currently visible near the edge of our observable universe will eventually disappear beyond our cosmic horizon as space expands. This creates a future where increasingly large portions of cosmic history become permanently isolated from any possible observation or communication. Trace cosmic history backward toward the Big Bang singularity. As energy density approaches infinity and space contracts toward zero volume, Einstein's equations predict that time itself becomes undefined. Classical physics cannot describe what time means at the universe's origin point. The mathematical description of space-time breaks down completely in this extreme environment. New quantum theories of gravity will be required to understand temporal reality near the cosmic birth moment. The Big Bang represents more than just the beginning of space and expansion. It likely represents the emergence of time itself as a meaningful physical quantity. Before this moment, the concept of before may have no physical meaning whatsoever. This fundamental limitation suggests that time dilation effects near cosmic origins might reveal entirely new physics beyond Einstein's relativity theory. Self-driving cars cannot tolerate navigation errors larger than a few centimeters. These autonomous vehicles must know their exact position relative to lane markings, traffic signals, and pedestrian crosswalks with surgical precision. Current GPS technology provides accuracy within several meters. This level of precision works fine for getting driving directions to restaurants or shopping centers. But autonomous transportation requires dramatically better performance that pushes relativistic corrections to their absolute limits. Future navigation systems will use networks of ultra-precise atomic clocks positioned throughout urban environments. These local timing references will need relativistic corrections calculated down to picoseconds to maintain centimeter-level accuracy across entire metropolitan areas. Even tiny relativistic errors will accumulate into navigation failures that could cause accidents or traffic chaos throughout automated transportation networks. Scientists now build optical clocks so precise they can detect gravitational time dilation across distances smaller than the width of a human hair. These quantum timepieces use individual trapped atoms as pendulums, oscillating hundreds of trillions of times per second. Such extraordinary precision opens entirely new applications for relativistic time measurements. These clocks can sense tiny gravitational changes caused by underground mineral deposits, water table fluctuations, or geological activity. Future quantum clocks will revolutionize geology, archaeology, and natural disaster prediction through time-based sensing. Advanced optical clocks will detect the passage of underground rivers by measuring microscopic gravitational time effects. They'll locate valuable mineral veins by sensing density variations that create measurable time dilation patterns across survey areas. This represents a completely new form of remote sensing technology based on Einstein's insights about gravity's effect on time flow. Imagine constructing a space elevator stretching from Earth's surface to orbit at an altitude of 36,000 kilometers. Different sections of this massive structure experience significantly different gravitational time dilation effects. The bottom experiences stronger gravity and slower time. The top experiences weaker gravity and faster time. Engineers must account for these relativistic effects when designing structural components and control systems. Without proper time synchronization, the space elevator's different sections would operate on incompatible time standards. Communication signals between the ground station and orbital platform would gradually drift out of phase due to cumulative timing errors. Elevator cars ascending and descending the structure would lose coordination with traffic control systems. Managing relativistic time differences becomes a critical engineering requirement for any construction project spanning significant gravitational gradients in space. Launch toward the nearest star system at 90% light speed. Your 20-year journey to Proxima Centauri takes only about 9 years from your perspective aboard the spacecraft. This time dilation effect represents the only known method for humans to reach distant stars within single lifetimes. Without relativistic time compression, interstellar exploration would remain impossible for biological travelers. High-speed space travel transforms time dilation from curious physics effect into practical exploration strategy. Future interstellar missions will deliberately exploit time dilation to enable human crews to survive journeys that would otherwise require multiple generations. The faster the spacecraft travels, the more time compression benefits the crew experiences. This makes relativistic time effects absolutely essential for humanity's expansion beyond our solar system into the broader galaxy. At extremely small scales approaching the Planck length, both quantum uncertainty and gravitational time dilation become so intense that current physics theories break down completely. This represents the ultimate frontier for understanding time's true nature. Quantum mechanics demands that time intervals become uncertain at these microscopic scales. General relativity predicts that gravitational effects become infinitely strong. These two requirements contradict each other fundamentally. A new theory of quantum gravity must resolve this conflict to understand time's deepest properties. Scientists working on string theory, loop quantum gravity, and other approaches seek to unify quantum mechanics with Einstein's curved spacetime. The successful theory will reveal whether time itself emerges from more fundamental quantum processes or represents a bedrock feature of reality. This represents the ultimate limit for time dilation applications, beyond which entirely new physics governs temporal phenomena throughout the universe.